How's it going? I remember I've always wanted to be an engineer. Engineering runs in the family, actually. My grandparents were engineers. I have engineers on my mom's side, my dad's side, all over. My first love fell in love with engineering when I was a kid. I grew up building all sorts of things. And one thing in specific that I really found interesting was prosthetics. So, as a kid, my first prosthetic I ever made was just based on a YouTube video. This YouTube video was of those cardboard hands made of straws, strings, cardboard, tape, stuff like that. Very simple. But eventually, I got more interested and more excited to keep going. So, I built one out of Lego Mindstorms, which is the engineering version of Legos. And I was really proud of this. This was around the age of 11, and I built it out of the Lego Mindstorms, which had a sensor on the front to open and close automatically. It's been a while since I built anything like this, but now as an Lehigh engineer, I have the opportunity to continue, and I'd like to build something a little more impressive. And so, going off of a rough sketch and a basic idea, I started building a cardboard prototype. I wanted to start by building this just to get an idea of what it would feel like. I wanted to make sure I knew all the measurements and stuff like that, make sure the hinges worked, make sure the cardboard worked as a good model for when I'd be building the actual product. But unfortunately, all I had around my dorm were a bit of tape, cardboard, some thumbtacks, and eventually you'll see Q-tips, which had to work as the hinges. Now, the pencil functions as the tricep, and a rubber band functions as the bicep. You'll see why this comes into play eventually. So, ready to start building, I made my first trip to Home Depot and picked up some aluminum. And after a lot of bending, sawing, sanding, screwing, and drilling, I finally had what started out as a forearm, but after a few days, turned into a full exoskeleton. And here we are, back where it all started. Let's get rid of this. This is the full metal exoskeleton I made. Obviously, for the sake of time, I could only make one arm, but maybe in the future I'll make more. As you see, the springs function as the rubber band, like I said, working as the bicep. But where's the tricep? Here's the gas spring. Now, unfortunately, I really wanted to use this. As you can see, what happens is, under a constant load of 22 pounds or 100 newtons, it compresses, and then it uncompresses. So, why didn't I use it? Well, the biggest problem is the range of motion. At the most open position of the arm, or at the most contracted, I guess, it's pretty good, but when my arm was open all the way, if I tried to get the spring on, it was far too short. This meant I could only get like half of the range of motion that I was desiring, so unfortunately I had to scrap it, but I'll still be using it for my calculations. One thing I wasn't sure of when I started designing this was, do I want this to be an exoskeleton or a reverse exoskeleton? What do I mean by that? Well, an exoskeleton is one that usually helps you lift weight. Something like, if you wanted to curl 100 pounds or something crazy like that. But I didn't really know how I would do this. There are things that can work as mechanical muscles, but with my level of expertise, I don't think I was able to make these in time, so I decided to use the springs and the gas springs. Now, one thing I realized as well is a reverse exoskeleton is just an exoskeleton, but with the functionality of the biceps helping you push things, and the functionality of triceps helping you pull things, the opposite of what you'd expect. So, this leads to two different variations. I could resist the motion from pulling, or I could resist the motion from pushing. And I could do this with both the springs and the gas springs. You'll see this in the calculations. So obviously for the closed position, there's going to be no force acting on the bicep at all. But in the open position with the spring, first I calculate the force due to the spring, and then I use the angle that it creates with the forearm to calculate the amount of pressure I have to push down is about 14.76 pounds, and the reaction force is about 5.74 pounds. Using the gas spring, I can do the same. The force from the spring creates a reaction at the pin, and the amount of force I need to push down is about 5.5 pounds. Using this information, considering there are 2 springs and 2 gas springs, the total amount of force that I'd need to push down, or that could help me lift up, is about 40.47 pounds. That's not bad. Now, why did I make the bottom section look like this? Well, as you can see, aluminum is not too hard to bend. So, let's calculate the maximum deflection. First, I look for the I value of the cross section. Here I calculate it as 0.094. Then, using Appendix F from the textbook, I could just plug and chug and find that the maximum deflection is only 0.167, and after I use the other version, with just the flat bar, it would be 130 inches. Quite a bit of a difference. Now, one thing I was worried about is how much force the screws would be able to hold for the hinges. Last thing I'd want while wearing this is for it to completely snap on me. According to my calculations, with both springs, I should be able to lift about 30 pounds extra. What could I use that would be 30 pounds? Weighing in at 167 and putting on a very, very full backpack makes me 197. So let's test it out. As you can see, it's not too bad to curl, honestly. Pretty light. The only problem is, it's only light at the bottom. At the closed position, since there's no resistance, I'm still curling a full 30 pounds. I hope you enjoyed this video as much as I enjoyed making it, and I hope nobody sees this except for maybe my MECH 12 class. I learned a lot from this experience. It was really fun using practical applications for the MECH 12 equations and combining with something I love and have a passion for. Until next time, I'll see you guys.